Bismillahirrahmanirrahim. We are interested in obtaining the orthogonal projection matrix onto the intersection of the ranges of two given orthogonal projection matrices P1 and P2. P1 and P2 are matrices of size n by n. They are orthogonal projectors, so each is Hermitian and idempotent. Let's investigate the subspace of vectors that can be expressed as the sum of a vector in the range of B1 and another vector in the range of B2. Consider the n by 2n matrix, which has P1 and B2 as submatrices. Consider vector y in the range of this matrix. Since y is in the range, we can write y as the product of this matrix and a 2n-dimensional vector. Suppose that the top n elements are n-dimensional vector x1 and the bottom n elements are n-dimensional vector x2. Y is equal to B1 x1 plus B2 x2. This is a vector in the column space of B1. That vector is in the column space of B2. Thus y is the sum of two vectors, one in the range of B1 and another in the range of B2. The range of this n by 2n matrix is a subset of this subspace. Any vector in this range is always expressible as a vector in the range of B1 plus a vector in the range of P2. Now consider vector y in this subspace. Y is y bar plus y tilde. Y bar is in the range of P1, y tilde is in the range of P2. Y bar is P1 times vector W1. Y tilde is B2 times vector W2. We can write this or that because y bar and y tilde are respectively in the ranges of P1 and B2. So y is P1 W1 plus P2 W2. We can write y as the product of this fat matrix and the 2n-dimensional vector constructed using W1 and W2. Y is in the range of this matrix. This subspace is a subset of the range of this n by 2n matrix. These two subspaces are identical. This implies they have the same dimensionality, so the dimension of this subspace is the dimension of the range of this matrix, which is its rank. Consider the range of the sum of the two orthogonal projection matrices. A vector y in this range implies that there exists n-dimensional vector z such that y is this matrix P1 plus P2 times z. Expanding, y is P1z, which is in the range of P1, plus P2z, which is in the range of P2. The range of B1 plus P2 is a subset of this subspace. The subspace of vectors that are a sum of two vectors, one in the range of P1 and the other in the range of P2. Let's investigate the dimension of this subspace. The dimension of the range of the matrix is the rank of the matrix. So we have here the rank of B1 plus P2. Both matrices are idempotent. Each is equal to its square. So we can put P1 here and B2 here. P1 squared is P1, P2 squared is P2. The orthogonal projectors are also Hermitian. We can write this P1 as P1 Hermitian, that P2 as B2 Hermitian. The matrix B1 B1 Hermitian plus B2 B2 Hermitian can be written as the n by 2n matrix with submatrices B1 and B2 multiplied by its Hermitian, which is of size 2n by n. If we have a general matrix A, the rank of A is equal to the rank of A Hermitian is equal to the rank of A Hermitian A is equal to the rank of A Hermitian. We have here the rank of the matrix times its Hermitian, which is this 2n by n matrix. So the rank is exactly equal to the rank of this matrix. We have established that this rank is the dimension of this subspace. Consider a vector space V and two subspaces S1 and S2. If S1 is a subset of S2, and the dimension of S1 is equal to the dimension of S2, then S1 is S2. We have the same situation here. The range of P1 plus P2 is a subset of this subspace. We have just proved that the dimension of this subspace, which is the rank of B1 plus P2, is the dimension of this subspace. These two subspaces are the same. This is the main conclusion we got on the first page. If we have matrix A not necessarily square, the orthogonal projector onto the range of A is the matrix A times the Moore-Penrose pseudo-inverse of A, denoted by A dagger. A dagger is the orthogonal projection matrix onto the column space of matrix A. If we want an orthogonal projector onto this subspace, and since it is the same as the range of P1 plus P2, then the orthogonal projector can be written as B1 plus P2 multiplied by the Moore-Penrose pseudo-inverse of B1 plus P2, P1 plus P2 dagger. In our case here, the orthogonal projector can also be written as P1 plus P2 dagger times P1 plus P2. To see this, consider an n by n Hermitian positive semi-definite matrix A, which has this eigen decomposition. A is Q lambda Q Hermitian. Lambda is the diagonal matrix containing the eigenvalues of A on the main diagonal. The eigenvalues are real valued and non-negative. The associated eigenvectors are the columns of matrix Q. Matrix Q is unitary. Q Hermitian Q is equal to Q. Q Hermitian is equal to identity of size n by n. The inverse of Q is Q Hermitian. The eigenvalues of A are non-negative. The number of strictly positive eigenvalues is the rank of A. We can write A as a diagonal matrix S, whose size is the rank of A by the rank of A. We keep the eigenvectors associated with the strictly positive eigenvalues. This is also the reduced singular value decomposition of matrix A. A dagger is Q tilde S inverse Q tilde Hermitian. The inverse of S is simply a diagonal matrix with the reciprocals of the strictly positive eigenvalues of matrix A. If we multiply A dagger, we find that this product is identity of size rank of A by rank of A. Recall that the columns of Q tilde are orthonormal. S times the inverse of S is identity. This product is Q tilde Hermitian. But also A dagger A is Q tilde Hermitian. Here is A dagger, here is A. This product is identity. S inverse times S is another identity. Like in this case, we also get Q tilde Hermitian. A dagger is equal to A dagger A. Our orthogonal projection matrices are Hermitian. Their eigenvalues are either 0 or 1. So P1 is Hermitian and positive semi-definite. The same applies to P2. Their sum is Hermitian and positive semi-definite. Thus, P1 plus P2 times P1 plus P2 dagger is equal to P1 plus P2 dagger times P1 plus P2. This subspace contains the vectors that are the sum of a vector from the range of P1 and another from the range of P2. So the range of P1 is a subset of this subspace, as any vector in the range of P1 can be written as itself plus the all-zero vector. The all-zero vector is an element in every subspace. If matrix C is an orthogonal projection matrix and vector Z is in the range of C, then CZ is equal to Z. So this orthogonal projector, when multiplied by matrix P1, the result is P1. Take the Hermitian of both sides. Orthogonal projectors are Hermitian matrices. If A dagger is the Moore-Penrose pseudo-inverse of A, then by definition, A dagger and A dagger A are Hermitian matrices. So when we take the Hermitian of both sides, we get P1 multiplied by the projection matrix. The projection matrix itself can also be written as P1 plus P2 dagger times P1 plus P2. Matrix P1 is equal to this. It is also equal to the product of these three matrices. When we expand this side, we get P1 times P1 plus P2 dagger times P1 plus P2 times P1 plus P2 dagger times P1. When we expand this part, we get P1 times P1 plus P2 dagger P1 plus P1 times P1 plus P2 dagger P2. These parts go away. We conclude that P1 plus P2 dagger P1 is equal to P1 plus P2 dagger P2. Define matrix omega as double this matrix, which is equal to double that one. We can also write omega as the sum of this matrix and that one. From here, the range of omega is a subset of the range of P1. Any vector in the range of omega can be written as 2P1, B1 plus P2 dagger, P2 times some vector U. This is P1 times some vector. The range of omega is a subset of the range of P1. From here, it is also a subset of the range of P2. This means that the range of omega is a subset of the intersection of these two subspaces. Let's call this orthogonal projector P tilde. It is the orthogonal projector onto this subspace, which is also the range of this n by 2n matrix, which is also the range of the sum P1 plus P2. Let P be the orthogonal projector onto the intersection of the range of P1 and the range of P2. This is our target. This intersection is a subset of the range of P1. If an orthogonal projector is multiplied by a vector in its range, we get the vector back. If we multiply P from the left by P1, we get P. The intersection is also a subset of the range of P2. P multiplied from the left by P2 is equal to P. We can take the Hermitian of both sides here and there to show that P, the orthogonal projector onto the intersection, is P1P, PP1, P2P, or PP2. All these are equal. Each one of those ranges is in this subspace. P tilde is the orthogonal projector onto this subspace. So P tilde P is equal to P. Taking the Hermitian of both sides, we obtain that P tilde is equal to P. The range of omega is in this intersection. P omega is equal to omega. We can write omega as double this matrix or double that one or the sum of the two. Let's use the sum here. P1 is equal to P. P2 is also equal to P. We can take matrix P as a common factor on the left. Then we have B1 plus P2 dagger times P2 plus B1 plus P2 dagger times P1. We can take P1 plus P2 dagger as a common factor on the left. So we have P1 plus P2 dagger, B1 plus P2. This is matrix B tilde, the matrix which orthogonally projects onto the subspace of vectors expressible as a vector in the range of P1 plus a vector in the range of P2. P times P tilde is equal to P. Omega is equal to P. The orthogonal projection matrix onto the intersection of the range of P1 and the range of P2 is omega. It can be written in any of these three forms.